Welcome! Today, we're exploring how tiny chemical clues in ancient Roman glass are revealing the vast economic networks of the Roman era. It's all thanks to a technique called isotopic analysis. By examining the unique isotopic signatures of elements within glass, researchers can trace the origins of raw materials like sand, flux, and stabilizers. This shines a light on trade routes, production hubs, and the sheer scale of the Roman glass industry. Several key isotopes offer unique insights. Neodymium isotopes are fantastic for tracing the geological origin of sand, the main component of glass. Different sand sources, say from the Eastern Mediterranean like Egypt versus the Western Mediterranean, have distinct neodymium signatures. This isn't usually affected by recycling, which is a bonus. Then there are strontium isotopes, which help identify the source of lime used as a stabilizer. Often, this points to marine shells. Variations can indicate other sources, and recycling can affect these signatures. More recently, hafnium isotopes have been a game changer, successfully distinguishing Egyptian Alexandrian glass from glass produced in other Mediterranean regions. Antimony isotopes also play a role, helping trace the origin of antimony ores used as decolorizers, suggesting that only a few sources supplied the entire Roman glass industry. So how does this help us understand Roman economic networks? The invention of glassblowing in the 1st century BCE transformed glass from a luxury to a common good. Isotopic studies confirm that large-scale primary glass production, meaning the initial melting of raw materials, happened in specific regions like Egypt and Syro-Palestine. This raw glass was then traded in chunks to secondary workshops across the empire. But it wasn't an exclusively Eastern Mediterranean operation. Isotopic evidence also supports ancient accounts of primary glass production in the Western Roman Empire, possibly using local sands from Italy or Gaul. The Romans were also avid recyclers. Isotopic analysis can sometimes identify recycled glass through mixed signatures, showing how efficiently they reused resources. The field continues to advance. Researchers are combining multiple isotopic systems, integrating data with archaeological evidence, and building vast comparative databases. There is ongoing work to refine the differentiation between sand sources and to understand the full impact of recycling. Newer isotopic systems, like hafnium, are proving invaluable. For instance, hafnium isotopes helped pinpoint Egypt as the origin of the coveted colorless Alexandrian glass. In essence, isotopic analysis of Roman glass is a powerful tool. It takes us beyond just looking at ancient artifacts, allowing us to reconstruct the intricate economic and technological systems that supported one of the empire's most significant industries. By tracing materials from source to final product, and even through reuse, we get a detailed picture of Roman trade, innovation, and economic life.